Today we work on vector basis, and so let's start from the basic ideas from 3D space. So we have a coordinate system, vector basis. Here we have a coordinate system, Cartesian coordinate system, x, y, z. And the first concept is a radius vector. A radius vector. A radius vector is a vector. If you have here a point P with coordinates x, y, z, so vector a radius vector r vector is a vector which joins the origin of the system of coordinates, or 0 point, and point P. So and the head point of this radius vector is this given point P. So P has components coordinates x, y, z. A radius vector has components, the same numbers, x, y, z. It's very clear how can we get these numbers, because we can take away from the head point's coordinate tail point's coordinates, and tail point's coordinates here 0, 0, 0, since that the components of the radius vector are equal coordinates of the P point minus zeros. So we have these number x, y, z numbers here. Okay, this is the first one idea here. The first one concept is a radius vector. Next one thing here, you can notice that x, y, z here, we can say that they are projections of the vector of the r vector of the radius vector to corresponding axis. So let's consider one thing here, 2D space, to make easier this concept. If we have x-y coordinate system here, and here we have a radius vector, point P. So here we have x coordinate of the P, y coordinate of the P, and here we have an angle alpha between radius vector and axis x. It's very easy to calculate that x equal the magnitude of the vector r times cosine alpha. And the same thing about y, but it is r times sine alpha. You know that it is about SOHCAHTOA rule. SOHCAHTOA rule. Sine, it is opposite side of the rectangle triangular or hypotenuse. Cosine, consequently, adjacent side, and tangent equal adjacent or opposite side. Okay, so it means that a radius vector in the very common situation has as the components of the vector projections. I do not like r cosine alpha, r sine alpha, and we have here that is r bar, and rz. I didn't calculate it, this one thing. It is z or rz, it's your choice. Anyway, rz is projection to the axis z. A projection to the of the to the axis, to the z axis. Okay. Also one idea. So now everything is clear here. So the bottom line here, radius vector is a vector which joins the origin of the system of coordinates, and its components are projection of this vector in the x, y, and z directions. Okay, next one idea. It's about vectors decomposition. Look, so I go back to the coordinate system, x, y, z coordinate system here. And new concept is orthogonal basis in the 3D space. Look, I can introduce three vectors in the direction x, y, and z, and the very popular denotation of these vectors, but you can pick out any way you like, but usually people identify them like I vector, j vector, and k vector. They are unit vectors, and they located in the directions x, I is in the direction x, j in the direction y, and k in the direction z. And they are unit vectors, so we can say that I vector, the magnitude of y is 1, the magnitude of j is 1, and the magnitude of k is 1. So they are unit vectors. Vectors. Okay, and this is the first one condition, and the second one condition. So they have the same direction as the axis, and we can define their components. Vector A has components. It's clear that it is one component along axis x, 1, and the other components are zeros. J has components. X component is 0, y component is 1, and z component is 0. And k vector is 0, 0, 1 vector. The main idea of this orthogonal basis is that any vector A, any arbitrary vector R, it's better to use R because we are working with radius vectors, R, can be defined as a linear combination of the I, j, and k vectors, so that beside each of these vectors it has its component Rx times I plus Ry times j plus Rz times k vector. Here Rx, Ry, and Rz are components of the R vector. This denotation for R vector is an alternative denotation as the following one. R has components Rx, Ry, and Rz, has the same meanings as the summation of the linear composition of the I, R, J, and K vectors. Okay, let's check. Example. For example, our vector has components 2, 3, 4, for example. Okay, what component has these the linear decomposition of this vector R? Let's try to write down. If I input 2 times I plus 3 times j plus 4 times k, we can put in the substitute instead I, j, k their components view, and we have 2 times 1, 0, 0, 0 plus 3 times 1, 0 plus 4 times 0, 0, 1. And if you multiply and use the standard rules of operations on vectors, you can have 2, 0, 0 plus 0, 3, 0 plus 0, 0, 4, and it is 2 plus 0 plus 0, 0 plus 3 plus 0, and 0 plus 0 plus 4, and you have exactly the given vector 2, 3, 4. So you can notice that this denotation and this denotation, they are very the same things. So the main idea here, we can consider these 3 vectors I, j, k, I, j, k here, j, k are vector bases for 3D space. And it means that any vector in 3D space, that means that any vector R can be represented as a linear combinations of I, j, k, so that beside each of the vectors as a factor you have to put the components of the vector R. Okay. What next idea? And the next idea is that we can pick out any three arbitrary vectors for 3D space. An idea put here. An idea. We can pick out any three vectors. Any three vectors. I denote them like A1, A2, and A3 in 3D space. 3D space can work as a vector basis. So it means that we can represent R through the, I denote here, like, if you don't mind, lambda 1 times A1 plus lambda 2 A2 plus lambda 3 A3. So we can decompose our given vector through these three vectors. You can make a conclusion that for 4D space, you can, as a basis vector, you can use 4 vectors. In 2D space, consequently 2. In 1D space, when we have only one straight line as a direction of the motion of our some items, you can take one vector as a basis vector and represent any other vector through this one, multiplicating by number per special number. But it's not very true here. We have one restriction for these A1, A2, and A3 vectors. But vectors A1, A2, and A3 should not be coplanar vectors. And here we are facing with very new term, coplanar vectors. What does it mean, coplanar vectors? Coplanar vectors, they are vectors. They are coplanar vectors. They are vectors so that there is no plane which contains all of them three at once. It means that, I use the reading, it means that there is no plane which contains all the vectors A1, A2, and A3 at once. So, examples, I think. For example, we have the 3D space here. I do not like I, G, K. I can notice that the pairs of vectors, for example, I, J, and J, they belong to one plane. But vector K doesn't. So I can take I and J vectors and K as a vector basis. But For example, vector C vector belongs to the ij plane, and it is impossible to use I, J, and C as a vector basis. It means that any vector which is beyond the plane ij, I can't represent this vector through ij and c vector, because I need a kind of z component of this vector. Okay, so how can we check if three given vectors are coplanar or not? You will have so-called the mixed product of the vectors. This is the topic to be, but here I want to just write down this thing. Here we have a criterion of complanarity. Of three vectors. You will have so-called triple product. So if A cross product B dot product C equals 0, it means that A, B, C vectors are coplanar and can serve as a vector basis. This kind of job we'll do later, because currently you don't have a definition of the mixed product or triple product. It is the mixed product or triple product. 3D space. For 2D space, you can pick out two vectors as a basis if they are not parallel or parallel. So in 2D space, with these two vectors, or these vectors, 2D space, we have x, y. They can't be the basis of the vectors, so it means that two vectors which have the same direction or opposite direction, they can't be the basis vector for 3D space. It sounds like linear vectors. A and B shouldn't be a collinear pair of vectors. So it means, in other words, it means that they shouldn't lie at the same plane, for example. They shouldn't be parallel vectors. So that's enough for today, and our next work will be dedicated to one or two examples of this, or calculation about vectors decompositions.